All right, welcome to our fifth video in this unit on polynomials. Before we get into polynomials and the transformations of polynomials, I'd like to give you a second to try these 6 problems for our warm-up. Okay, so in number 1, there are a lot of ways to do this one, but I want to share one strategy with you, and that is, multiplication, the order doesn't matter, right? So we can actually multiply 2 times 5 first, which is nice because 2 times 5 is 10. Then 10 times 79 is 790. Number 2 here, 5% of 61. You could multiply 5 times 61 if you wanted to, or you could multiply 61 times 10 instead and then divide by 2 afterwards. Either way is fine. I'm going to do 10. So let's find 10% of 61 first, and then we'll take half of that. So 10% of 61 is 6.1, right? And then half of that, half of 6.1 would be 3.05. All right, what is the y-intercept of this function here? We've talked about this before when factored form, and really any form. If you put in 0 for the x's, whatever the output is going to be your y-intercept. So if you put in 0 for all these x's, you're going to get -1 times -3 is +3 times 2 is 6. So our y-intercept here is going to be 0, 6. All right, number 4, factor x squared plus 6x plus 9. This is actually a special one we've talked about before. You want to think of 2 numbers that multiply to give us 9, that add to give us 6. In this case, the 2 numbers that you're thinking about are exactly the same, in that they're both 3. Right? 3 times 3 is 9, 3 plus 3 is 6. So you could write it as 3 plus 3 times 3 plus 3, or you could write it as x plus 3. So anytime you multiply something by itself, you're squaring it, right? So you could write it as x plus 3 squared. All right, number 5, classic ACT problem here. Right, where you're given a function with a quadratic in it and you're asked to put in a negative number. A lot of mistakes happen here. So let's walk through it. So it's asking us to put -2 in for any x's up here in this function. There happens to be only one x. And so we're going to put -2 and we're going to square it. Make sure you put your parentheses. We're squaring all of -2 and then -3. -2 squared is actually 4. 4 minus 3 is 1. So 1 is our answer there. All right, number 6, increasing and decreasing intervals. I know this is kind of a rough sketch here, but our increasing would be so we'd increase from -infinity to -3 union. And we're going to increase from -1 to infinity as well. So that's our increasing interval. Decreasing would be decreasing in between -3 and -1. So hopefully that gives you some extra practice on that. All right, with that behind us, let's go ahead and move into our topic for today, which is transformations of polynomial functions. So our goal is to describe transformations of polynomial functions and really any graph. What we're going to talk about today applies to any function no matter what. So that's why today's topic is so important, because we can apply what we learned today to any function type. Hopefully you've seen kind of some of these ideas before back in Integrated 2, but let's go ahead and get into it today. We're going to talk about translations, reflections, stretch, and compressions. So let's get into translations. So translation is simply just shifting the graph either left or right, up or down, just picking it up and moving it one way or the other. The shape stays the same, the size stays the same, everything stays the same except for the position in the graph. So to get at this idea, I want to first have you think about a series of problems. All right? So I want you to think about what value would you put in for x here so that it would output 0? So what value squared would be 0? And hopefully you're thinking 0, right? So 0, an input of 0 outputs 0. All right? So let's change the function a little bit and let's see how it impacts things. So now we have x minus 4 quantity squared. What value would I put in for x here so that it would still give us 0? So think about that. All right, if we put in 4 here, 4 minus 4 is 0. 0 squared is still 0. So inputting 4 still outputs 0. So 4 gives us 0. All right, so let's think about this last one here. What value of x would still produce 0? Hopefully you're thinking negative 6. Negative 6 plus 6 is 0. 0 squared is still 0. So this idea that we're like undoing what's in there with the parentheses, right? So we had to put in not 0, we had to put in 6 less than 0 in order to still get out 0. In this one, we didn't put in 4 less than 0, we put in 4 more than 0 to counteract the negative 4 that's in there. So we're undoing what's been done in the parentheses. And so what happens here is when we replace x with x minus 4, you might think that shifts to the left 4, but it's actually the opposite. It shifts to the right 4 because, again, we're undoing what's been done in the parentheses. Same thing here. Going from 0, 0 to negative 6, 0, that's just shift left 6, when you might think it might be to the right 6 because of the plus 6. So it's kind of the opposite of what we might think, but I want you to really understand why. We're undoing what's been done to x. All right, let's look at another example. A little more complicated now. All right, so now we've got this polynomial up here. It's a quadratic. And putting in 4 into this quadratic gives us 57. So we want to think now, we've replaced the x's with x plus 7. So both those x's, we put in x plus 7 for both of those. What value could we put in for x so that it would still output 57? So let's think about that for a second. We still want it to output 57. And we know that when we put in 4 in for x, we should get out 57. So what we're thinking about here is, if this were still 4, and this were still 4, we should get out 57, right? Because we of what we set up above. Well, what value of x would make this still be 4? Well, let's see. Negative 3 plus 7 is 4, right? Negative 3 plus 7 is 4. And then we know that by having 4 in those positions, it outputs 57. So negative 3 produces 57 down here with this function. So let's see what the difference was here. Well, right, we replaced x with x plus 7. But what happened to the x value we had to put in to get out the same output? Did we put in 7 more than 4? No, we actually put in 7 less than 4 in order to get the same output value. So that's why when we replace the x's with x plus 7, it actually shifts it to the left 7, not the right. Okay? So we're talking about translations right now, left and right. When we replace x with an x plus 7 or an x minus 4 or x plus 2, something like that, it's going to shift it to the left and right, but opposite of what we might think. So let's think about this one here. So the parent function here is the absolute value of x. So we have y equals absolute value of x. And we've made 2 changes to the function. One is we've replaced x with x plus 3. The second one is we added 4 to the end. All right, so think to yourself, what might those 2 change about the function? Yeah, so first of all, x minus 3 in for x, that's going to shift it to the right 3. Again, we're undoing what's been done inside with x. This plus 4, so we get all these output values that are now shifted to the right 3, and then all of a sudden we add 4 to every single output value. If we add 4 to every single output value, that's going to shift things up 4. So inside with x shifts left and right. Once we're outside the function and we add or subtract, then that's going to shift things up or down, like we think. So on the inside it's kind of opposite, but on the outside it's exactly like we might think. All right, so let's do one more, but more general this time. So if we have a function f of x, and we replace it with this new function, f of x plus 1 minus 6. So we don't even know what the function is, but we can still describe how this looks different than the original function. Again, going back to what we said earlier, this applies to any function type ever. Okay, so we can think about it generally. This is going to shift the function left 1 and down 6. Okay, so translations are fairly straightforward in it, that the inside is kind of opposite of what we might think. We're undoing things. And the outside is exactly like we might think in terms of the vertical position. So let's switch gears there for a second. Let's look at reflections. Okay, so with reflections, there are two types of reflections. Let's look at the first one, f of negative x. If we think about what's happening here, we're negating every x value is really what happens here. Okay? So if we negate every x value, any x value that was to the right of the y-axis is now going to be to the left of the y-axis. Anything that was to the left of the y-axis is now going to be to the right. So we're going to reflect across the y-axis when we do negative x in for x. So it's going to reflect across the y-axis. If we take the whole function itself, f of x, and all the outputs from that, which are the y values, and we negate those, anything above the x-axis is going to now be below. Anything below the x-axis is now going to be above. So it's going to reflect across the x-axis. So you don't really need to memorize that per se. Just go back to that underlying idea that we're changing all the x values or all the y values, and what does that do to the function? So we can reflect graphs as well across the y-axis or x-axis. So let's think more in general now. So we have these 1, 2, 3, 4 things that impact a function in terms of transformations. We've talked about h. H is the horizontal. And remember, that's the one that's opposite of what we might think because you're undoing things. K is the vertical translations. A and B, they could be reflections, but there's a more general way to think about these. We're going to look at an example here in a second, but A is really your vertical stretch or compression. Whereas B is the horizontal stretch or compression. And again, we'll see what we mean by that here in just a minute, but if you think about a graph stretching vertically, it's really changing the shape of it. And so it's going to be extending further up or down or being compressed vertically or being compressed horizontally, things like that. Let's look at these two graphs, or look at these two functions. So shifting to the right one and up 3, but this graph is actually going to be compressed horizontally. So remember this, the B value, this is the 2 right here. Since we're having to undo things like we do with the horizontal translation, since we're having to undo things in the argument is what we call it with x, then a positive 2 is actually going to compress things by a factor of 2. So it's actually going to decrease by half. Okay, and then this 4 is the A value. It's going to extend things upward by a scale factor of 4. Okay, so it's going to be a vertical stretch of 4. So things going down, things going up from there. And then this last example, we don't even know what a sine function is, okay, in this course yet. But we can still think about what happens to the original graph of the sine. So it's going to shift it left 1, down 60. This one's actually going to be a horizontal stretch of 3, because we have to undo the multiplication of 1/3, so it's going to stretch it by a scale factor of 3 horizontally. And then this is going to be a scale factor of 2, so it's going to stretch it vertically by a factor of 2. So let's take a look at a Desmos example here that I've got on the screen. I hope you can see, and maybe I'll move closer here so you can see the functions themselves. So I'm starting out with this quintic function here. And I'm going to do a bunch of different things to it, and we'll see how the graph changes based on what we type in. So we have x to the 5th minus 3x squared minus 4x plus 2. The first thing I've done here is I've replaced all the x's with x minus 2. So I hope you remember what that does, right? That's going to shift it to the right 2. So let's turn that on, and you can see the graph there is shifting it to the right 2. All right, and then I'm going to turn that off here. Again, this dotted one is going to be our original, so we're always going to compare to that dotted one. Okay, so this next one, what I've done here is I've just tacked on a -3 to the end of the function. So it's f of x minus 3. Now you can combine these to be -1, but regardless, it's going to shift the original function down 3 units. So it's going to be exact same graph, right? It's exact same shape and everything. It's just shifted down 1, 2, 3 units for every single point on here. It's shifted down 3. All right? The next one, I've just taken the function and I've multiplied by 1/3 out in front. Again, that's our vertical stretch of compression. Since it's 1/3, it's going to compress things by 1/3. So let me turn that one on and let's see what happens. Yeah, so everything was divided by 3. So this y value here of 6 or 7 was divided by 3, and it gives us the new y value here. So every y value on the original was divided by 3 to give us this compressed graph of the same function. All right, up next, I've replaced every x value in the function with 2x. So that's our b value that we've talked about. It's actually going to be a horizontal compression. You might think it might be a stretch because it's a 2, but since it's in the argument with x, we're going to do the opposite, kind of undoing what we've been done to it. So it's going to compress it by a factor of 2, so really half everything. See how it's a lot more compressed now than maybe it was before. Let me turn on projection motion or mode here so you can see it. Yeah, right here. All right. And then next, we've talked about this one before. I've replaced every x value with -x. Remember what that does. If I replace x with -x, that's going to reflect it across the y-axis. So let's take a look at that. All right, so this one happens to be red as well, but you can see that this point became here. This point became here. This point became there. Everything reflected across the y-axis there. And then lastly, I've just negated the function out in front. So this is negative f of x. You could also distribute this negative into each term if you wanted to, but this is negative f of x. And you can see what it did here. Everything was reflected across the x-axis. So that reflection there that we've talked about. All right. So as you can see here, we've put to use everything that we learned about transformations into this one function, and hopefully you're able to see how each one impacted the graph. Okay. So to recap, again, keep in mind that everything we learned today is applicable to any function type. So linear functions, quadratic functions, absolute value, cubics, quartics, quintics, Everything that we've learned today applies to any of those and more. All right? So our goal was to describe transformations of polynomial functions and really any graph, and I think we've accomplished that through translations, reflections, stretches, compressions. In general, these are called transformations of a function. All right, so that's our goal for today, and I think we were able to accomplish that. In our next video, we're going to talk about more analysis of graphs by looking at what we call average rate of change. So we're going to do that in our next video. Hope to see you then.